Okay, so this is Junior Roberts coming to you with realjuniorroberts.com. In this video, we'll be looking at a worked example, right? So our question says that the figure below, right, which is this figure right here, shows a toy runway. Now, after a car of some mass is released from the point X, this point here, the model car runs down the runway, loops the loop, and travels toward point Z. And we're told that the radius of the loop is 2.5 meters, right? And we're taking gravity G to be 10 meters per second, right? So this is a question involving energy and forces, specifically centripetal forces. So let's look at what the question is asking us to do. So the first thing, part A says that ignore the effects of friction, outline the energy changes along the object's path. So we can make note of that, right? So at point X, we have potential energy, can label that PE, right? As it goes down the runway here and reaches point Y, we have kinetic energy, KE, right? It goes up, reaches point P, and then we have both potential energy and kinetic energy, right? After it completes the loop, it goes down to Z and then has kinetic energy, right? So this is the energy change throughout the path of the object. Now part 2 says what is the minimum speed the car must pass point P at if it is to remain intact with the surface. Now this is where we look at forces, specifically centripetal forces, right? So since the object is moving around the path here, right, it's moving around the path here, there's some force which keeps it along this path, and that force is what is known as centripetal force. So the formula for centripetal force, let me just make a note that we're looking at part B. So centripetal force, we can call that F centripetal is equal to mv squared over r, where m is our mass, v is the speed which keeps it in the loop, and r is the radius of that loop. Now, since we have an object of mass, right, going around the circle, and at point B we have a centripetal force acting on the body to keep it in the circle, and then we have the force due to gravity trying to kick the object out of its orbit, right? So for the object to remain intact, those two forces, the centripetal force and the force due to gravity, must be equal. So we can say for object, let's make a note here. So we can say for object to remain on path, right, we can say the force, the centripetal force, must be equal to the force due to gravity. So we can write an expression for that, right? So we know that centripetal force is mv squared over r. So we can write mv squared over r must be equal to the force due to gravity. And we can write that as mass times acceleration. Now, since we're looking at the same object in both cases, our mass will be constant. So our mass is essentially cancel. So we're left with our formula being v squared so we're left with the formula v squared over r is equal to a. Now the question wants us to find the minimum speed, and we know that the symbol for speed is v, so therefore we can go ahead and say that v squared must be equal to multiply both sections by r, so multiply by r there, multiply there by r, so we have v squared is equal to a times r. Now acceleration is the acceleration due to gravity, and r is our radius, but we're trying to find v, so we need to actually find the square root of both sides. So we simply say that the square root of v squared is equal to the square root of ar. Then we write that v is equal to the square root of a, which is 10 meters per second, meters per second squared, and our radius is 0.25 meters. Alright, so we can use our calculator, right, and then we can say the square root of bracket 10 multiplied by 0.25 close bracket, and that works out to be 1.58, and our units is meters per second. Right, so that would be the speed that which the object passes our point P. Now, the third part in the question wants us to find the minimum height to ensure the speed in B above. Right, so taking number 3, part C. So let me just redraw the setup again. So we have something like this, and then we have our loop there. Alright, now we have a height here, right, and let me just draw this properly. So that's our circle or our loop, and we're given that the radius, which is the point from any point from the center to any point on the circle, as 0.25 meters. That's the radius, right? So we realize that we just found the speed here, which is the speed at this point here, at point P, to be 1.58 meters per second. Now, because we're ignoring any effects of friction, we assume that the energy throughout the system is conserved. So we can look at it then as we have had a change in energy due to the change in height, right? So there's a height difference between point X, let me label it, point X, right, and point P. There's some height difference, and we can say that that height difference is h minus 0.5, which is the diameter of the circle, right? So if we agree here, we can write an expression for the conservation of energy. So we can say that change in potential energy is equal to the change in kinetic energy. Alright, so we know that for potential energy, our formula is, let me just get the pen here. our formula is mgh, and that for kinetic energy is half mv squared. Now, because again the mass is constant, our masses will cancel, leaving us with gh is equal to a half v squared. Now, the height here is actually h minus our radius, which is, h minus our diameter, which is 0.5. So we can say that g is 10. We can start to fill in our values now. G is 10, as we know, multiplied by h minus 0.5 is equal to a half v squared, which is 1.58 squared. And if we solve this, we get that h minus 0.5 is equal to, divide both sides by 10, we get that 1.58 squared over 2 times 10. Now we can further simplify this by saying that h minus 0.5 is equal to, let me get a calculator here, so we can say 1.58 squared divided by 2 times 10 is 20 equals that. Right, so we get 0.125. Right, then now we can say our height h is equal to 0.125 plus 0.5, which gives us an answer of 0.625 meters. Right, so that would be the minimum height in order for us to get the speed that we calculated in b above this speed, here. So this was a quick run through for a worked example involving forces and energy. If there was anything in this video that was unclear to you, please feel free to send me an email or post your comments below. Thank you for watching.